Hi everybody, Ryan again from the Headwaters Science Center, and it is 3:30, which means it is time for one of our 3:30 after-school STEM shows. And if you haven't been watching these, what we do with these is it's every day at 3:30, 7 days a week, we go live here at the Headwaters Science Center on Twitch, Facebook, and YouTube, talking about, or with one of our educators talking about some sort of STEM type of topic that we have some material for here at the Science Center that you might have a conversation about when you come here and visit the floor. And so, depending on the day, you might see something very different. You're gonna have different interpreters every day as well. And so today, you got me. I'm Ryan, and today we are going to be talking about fossils and fossilization. And so we have a handful of different fossils that you'll find out on the exhibit floor when you come and visit the Headwaters Science Center. There's a couple of them upstairs. We have a couple down on the ground floor too. We have more sort of casts down on the ground floor. So not quote unquote real fossils, but like I said, models of fossils. And so there's a lot of places you're going to encounter fossils around the Science Center. And so that begs the question, of course, of what is a fossil? What types of different fossils are there? How are fossils formed? What are they? And I'm sure, like, when you think of a fossil, there's a certain image that pops into your brain. You know, I think when someone says fossil to me, the image that immediately pops into my brain is like, okay, like a T-Rex skull is like the first thing that's like, okay, that's a fossil. And that's true, a T-Rex skull would be a fossil, but fossils also incorporate a lot of other different types of things that are formed a lot of different ways. And so in the most broad definition, the broadest definition of fossil would be any remnant of a formerly living thing that gets left behind after it dies. And so, I said that's a really broad definition. I mean, that would mean that, like, the second you're dead, you're a fossil. Like, if I keeled over right now, my body immediately becomes a fossil. And that arguably is true. But generally, when we think of fossils, we're thinking of stuff that's been preserved for a really, really long period of time, longer than, you know, the standard amount of time it would take for something to sort of decay and rot away. So we're talking about stuff that has been preserved for an abnormally long amount of time, generally, when we're talking about a fossil. And again, it's a fossil of a living thing. But that can happen a lot of different ways. That, like, T-Rex skull type of thing I mentioned is something that is a relatively common way that things will fossilize. Where generally, if you're seeing something like that, what it actually is not the bone. There's a sort of a understanding that a lot of people have is that a question I get asked a lot, let's put it this way, when you're talking about fossils, even if they're real fossils, is, well, is this thing real? And so, for example, we can look at this ammonoid fossil, for example, and someone could ask, is this real? Well, yes and no. There was an ammonoid at one point in history that was this size and this shape. This really did exist, but no part of that ammonoid is in this fossil. This is, for all intents and purposes, a rock that is shaped like an ammonoid that once existed. And so this is an example of a fossil that was formed basically out of a cast. And so what happens with that is you get a thing that dies and it falls usually on some sort of soft sediment, mud, sand, silt, whatever. Gets covered up by some more kind of softish sediment, again, more mud, more sand. So you see it a lot with underwater stuff. And then what happens is that softer sediment hardens and you get an imprint of what was buried in it that hardens and is in it. So it's kind of like when if you ever find like some wet cement and you put your handprint in it and that handprint stays there. That's kind of what happens with things like these. And you'll find fossils that are just those imprints every once in a while. In fact, they're relatively common. I was looking for one down in the basement and couldn't really find one that's exactly that, but we have some here that are sort of like that, where they're plant ones. And I'll just walk around for it. So you can see there's kind of an imprint of the plant that is just in the rock there. But every once in a while what will happen is there will be another step that occurs where you'll have those imprints, and those imprints will get filled with sediments, and then those sediments will harden themselves. And so those sediments end up hardening into the shape of the thing that was once there that made its imprint in the sediment and then decayed and went away and then I said, the imprint, the sediment was left. New stuff comes in, fills up that gap that old thing left, and you end up with a fossil of, or basically a cast of what that thing was. That's a very common way that we get fossils. That's like when you're going to a museum and you see like a big dinosaur fossil, more often than not, that's what you're seeing is a cast that was made naturally, but it is a cast of what was once real bone. But every once in a while you will get a little bit more direct fossilization that can happen. And so I have here is a piece of mammoth tusk that is fossilized. And something that's really interesting with this one that is a little different than what we'd probably see if we cracked open that ammonoid is you can see all these little holes. Can we see all those little holes? You can see all these little holes that are inside of it. And so that's a sign that this is probably a result of petrification rather than cast fossilization. And so what happens with petrification is, similarly, a thing gets buried very quickly after it dies, before it can really get a chance to be ripped apart, eaten by mice or whatever. But then over time what happens is water is going to get in to wherever that thing was buried, and water brings with it minerals, particularly brings with it a lot of silica, generally. And so what happens is over time that water kind of erodes away at what was once that mammoth tusk, and it erodes the old tusk away, and it leaves behind whatever minerals were in that water when it does so. And so this is, you can think of this almost like it's the same process that makes like a geode or like a stalagmite and a stalactite. Very similar type of process, except I say you're eroding away what was formerly a tusk and replacing it with a mineral component, like oftentimes silica. And so you'll see that occasionally. And what's kind of cool with that is it lets you get, I said, like kind of internal structures in a way that you don't with the casts, because the cast, by definition, is kind of just the outside, whatever was exposed on the outside at the time that thing died. You can't get, if we crack this open, it's just going to look like a rock in there. Whereas if we crack this open, it's going to look like the inside of a mammoth tusk. Now, I talked a little bit earlier about those sort of impression fossils, where they're not so much the direct remains of a thing, but they are a sign that a thing was once there. And you'll see these for a number of different contexts. Like I said, plants is a lot of times the way you see it as. The other thing you'll find a lot of times is like footprints that are this way, where there's nothing died there to get buried, but it left behind some sort of trace that a thing was there. We call these trace fossils. And it can be things like footprints. It can be, like I said, some sort of impression that something left. Anything that an animal would have left behind. So like fossilized animal poop is a thing. They're called coprolites. One of the other really cool ones that one of my favorite examples of trace fossils is that you can find the stomach rocks of dinosaurs sometimes. So like a lot of the big long neck sauropod dinosaurs would swallow rocks to help them digest their food. And so when those things die, those rocks get left wherever they died. And so you'll find these little bundles of rocks like in the center of a dead sauropod every once in a while. And those rocks would arguably be considered trace fossils. And so that's kind of what we're seeing with these plant ones, like the one I showed you earlier. There's a little something extra on these ones, where when you look at them, you'll see it's not just an imprint, but there's actually a little bit of a like coloration to it as well. Where you're seeing kind of that black outline. You'll see it on really all these ones, all these plants that I pulled out, is that black color associated with it, more so than just the imprint. And what that is carbon. And so what can happen is a thing dies, and then certain elements that made up that thing once upon a time get taken away, or not everything decays at the same rate. And so you're talking about a plant, it's made up of a whole bunch of different stuff. There's some oxygen mixed in there, and some nitrogen, and some phosphorus, and whatever. And that stuff all gets taken away. That stuff all decays and goes off into the ether. But it leaves behind other certain elements that if it doesn't get disturbed are going to last a lot longer. So carbon is a good example of that. And so that black coloration that you're seeing is carbon that's been left behind by when a plant was at some point there, where everything else that once made up that plant has gone away. So you're seeing this outline where the carbon was concentrated. So you're seeing it along like the middle part of the leaf and on the little, I should have looked up the names for these things, but the leaf bones, the little things that make up the middle parts of the leaves. So yeah, different type of fossil there where it's more of an elemental, leaving behind trace amounts of elements that once made up that thing. The fossil, or the petrified wood I have over here, would be made a very similar way to what the mammoth tusk was, where you would have minerals getting into that after it died and replacing the organic elements with a mineral element, and so that's generally how petrified wood is made. I have a couple trilobites here, and these would likely have been made by the first method we talked about, like the ammonite, where got buried, some mineral came in there and filled up the place that it was after it decayed, and then hardened and turned into the shape of a trilobite. But another really cool one that we have here, all of our Jurassic Park fans out there will know this, where we have what's called amber. And amber is a fossil in its own right. It's fossilized tree sap. But what can happen with amber, and this particular piece doesn't have anything in it, but what will occasionally happen is small critters, mostly insects, will get stuck in the amber and die, and then that amber will fossilize, and so that bug will be stuck in that amber after it fossilizes. And so, like I said, like in Jurassic Park, this is where they found the blood for making their clones, was in a mosquito that was stuck in amber. And so, like I said, ours doesn't have any in that. This is just a little piece of amber. But you end up with something that looks a little something like this. And this is not amber. This is some kind of acrylic that has a scorpion in it that we sell in the gift shop. But just to give you an idea of kind of what the type of thing we're looking at here is the acrylic, the clear stuff, would be tree sap. And then something small gets stuck in the tree sap and dies. And then, like I said, the amber hardens. And that's really cool because it'll preserve like the whole critter. And one of the things that's really true about fossils and fossilizations is it really, really, really disproportionately favors things that are big. So, you know, when we think about the stuff that's alive back in that time of the dinosaurs, we think about, you know, the Jurassic Cretaceous period. The things that probably pop into your mind are all these like big reptiles. It's dinosaurs, it's triceratopses and T-Rexes and things like that. But it's very likely that there was also a lot of little stuff going around at the time that we just don't really know about. Because if you think about it, what's more likely to last a long amount of time? Something that has a shoulder blade that's this big, or something that's that big. And so amber is really cool because it gives an opportunity for these little teeny tiny things to like get caught and be preserved really well in a way that, you know, you would never really see with a big thing like that, other than, you know, when you get into like tar pits and stuff like that. But it helps us get a better idea of kind of what more of the animal taxa of the time were like. Because like I said, if you're just looking at like the big fossils, stuff like this, it's going to be more favorable to big animals. They're more likely to keep than little stuff is. Even with big animals, the big parts keep a lot better. You're a lot more likely to find a mammoth scapula, shoulder blade, than you are to find the inner ear bones of a mammoth. We don't find those because they're small, they get broken, they get walked off with some sort of little rodent or whatever that finds the remains. They get destroyed very easily, very commonly, or otherwise swept away, and leaves the big things behind. And so we tend to have kind of a skewed idea of what the world was like because we only see the big stuff. It'd be like if we imagine that like the only animals that were alive today were elephants and tigers. And it's like, well, that's not true. In fact, it's not even close to true because most of the animals that are alive today are, you know, ants. You know, if you talk about how much biomass that animals make up in the world, like over half of it is insects. But that's not necessarily going to be reflected in the fossil record 100 million years from now. So I said, it's one of the things that's really cool about amber in particular is it is the one type of fossilization that really disproportionately shows us small things rather than big things. And I think we'll take a quick look at this thing up front here. This is kind of a unique one that we have. This is out on the exhibit floor all the time. This is upstairs. Anytime you want to come and check it out, you can. And this one's kind of unique because this has fossils kind of in their original context. So if you were to be doing work as a paleontologist, is what we call someone who goes and digs up old fossils, the paleontologist. When you find stuff, you don't just rip it out of the ground right away and, you know, throw it on a shelf in a museum basement. You got to document where you found it. It's very important to this whole process, is documenting where things are. So you do what's called pillaring when you're excavating things. And you can see that on here, where you can see how we have all of these fossils are at different elevations. And so what you do is you excavate underneath, leave this little pillar underneath, so that when you're taking your notes, when you're taking photos or whatever, it's documented how deep they were and where all these things were in relative position to one another. And so at this point, assuming all this stuff got documented, would be when you would start collecting them and packaging them up and sending them back to the lab, wherever that lab may be, for further processing. Or you might do something like this, where you polish it up and you send it to a museum to be an exhibit. And what we have here, if you're curious about what we're looking at, are a couple of different types of mollusks. So mollusks are things like snails and squids and octopi, things like that. Are snails mollusks? Yeah, whatever. And stuff like this is actually relatively common in Minnesota. Minnesota was underwater for much of its history. And so particularly these kind of long, skinnier fossils are something that's kind of iconic for Minnesota. The name escapes me right this second, but basically what they are a type of like sort of squid-like thing that had a hard shell on it. And we have some smaller ones here, but these things actually got to be pretty big. So if you ever are down in St. Paul and visit the Science Museum, Minnesota, they have one of these shells that is probably 5.5 or 6 feet tall, down in their dinos and fossils area. At least they did last time I was down there. But it's kind of cool because you don't see squids that have like a hard shell anymore. It's not a thing. You know, you don't see very many free-swimming animals at all that have hard shells these days. It's pretty much just nautiluses are really the only free-swimming shelled thing we have these days. But it actually used to be a much more common thing. And so, but shells are heavy and tend to not float very well. So what you have to do is figure out some way to haul that shell with you in such a way that it makes it actually, one, able to be moved with, but actually worth keeping as well. And so what the speculation is, what the theory is that they would be full of like gas. And so they would basically be able to treat their shell very much like a modern fish treats its swim bladder, where they can add or remove gases from the shell in order to kind of adjust their buoyancy. And so you can imagine like I said, a pretty substantial squid that has a big, heavy shell on it that's able to move gas in and out of it pretty freely. It's kind of neat. And like I said, it's an animal that absolutely existed in Minnesota. And as far as time period, when we're talking about stuff like this, hard to say exactly because a lot of these critters exist for 100+ million years. But this could very well be a 500 million year old slab of rock here. Like this could be Permian, or it could be a little bit more recent than that. I would guess this is pre-dinosaur regardless. So somewhere between 500 million and 300 million years ago probably is when this would have been first set down, when these critters died. So probably the oldest fossils we have here, maybe even. I don't know, it kind of depends on how old our fossilized blue-green algae is. But that stuff still exists. Not the oldest critters we have. Definitely the oldest thing that you're going to see out on the exhibit floor. This thing here, because like I said, you're talking at least a few 100 million years ago with it. And I think that's pretty cool to be able to see, and even, as long as you're careful, touch something that's that old and documented at that old. And I don't know. I think that's really cool. I expect that most people would think that's cool too. So next time you're visiting the Science Center, you can come and check it out. Like I said, it's up on the top floor, kind of right above where the gift shop is. And so I think if we don't have any questions or comments from the chat section there, I think we'll call that a wrap for this one. Thank you all for watching. We are open right now from 9:30 to 5:30, Friday, Saturday, and Monday. And we are open from 1 to 5:30 on Sundays. So if you want to come and visit, you want to see some of these fossils that are out on the floor, maybe get talked to a little bit about them, maybe meet me out on the floor. I'm here all those days too. Like I said, we'd love to have you come in, and if you happen to come by at 3:30, we might be doing one of these shows. In fact, we will be doing one of these shows, and you might get a chance to participate in them. We're always happy to have a few guests here to lob questions out to. Makes it more fun for me, more engaging for y'all probably too, if I have somebody I can bounce off of here. So yeah, come by in the afternoons. We'd love to see you. But otherwise, thank you all for watching, and it'll be James tomorrow.